Much.
Yeah, thanks a lot. Do I need to switch on my microphone, or is it on? It's on. Okay, perfect. So happy to be here. My name is Niklas from Just Quantum. The title is actually a little bit outdated. We are going to present you a quantum-first software framework and macroeconomic modeling and things behind like HHL and phase estimation is one of the specific use cases you can do using our software. And a collaboration together with Wadim from Bundesdruckerei is another kind of use case which leverages the full software. So be a little bit clear, the setting with the title is not really specific. The present, yeah, okay. So I'll quickly give the word to Wadim.
Thank you, Niklas. Hi, my name is Wadim. I'm from the Bundesdruckerei. If you don't know us, if you haven't been here in the early morning, there was already a presentation by us. But to make it short, we are in everyone's pocket if you're German, so we print the IDs, but more generally, we print security. So this is our domain, and our task is to keep security secure. So one of the aspects that we are trying to understand is how quantum will affect security in the future. And so we are always looking for partnerships and for good projects in the case with sovereign results, let's say it like that. We are very happy that we, a couple of years ago, found such a partner, and we explored many use cases, but one in particular was rather fruitful. So what we did with Just Quantum is to understand how quantum communication can be explored with quantum software. And it was a blast. We wrote a paper about it. It was just published. And the idea here is to understand quantum key distribution protocols as quantum circuits. But not only that, it is the ability to give everyone here in this room, and especially the people in the ministries who are supposed to maintain sovereignty, the ability to understand the QKD protocols as quantum circuits without knowledge about quantum. So this was a very difficult task. And I'm very, very happy that it worked out. So you will see a part in the presentation about this use case. And this use case actually has a more broader application, which I will tell you later on today. So it's all working together. And but enough of me. Please, go ahead. Thanks.
Thanks, Wadim. So what we are doing as Just Quantum, well, we make quantum computing useful for the end users in the field of security finance. And we're actually here quite long already, since 2018, founded in Frankfurt. We have 3 offices now, Frankfurt, Berlin, Paris. We have 4 patents pending, own patents, and also shared patents with collaborators, and 13 team members in the field of mathematics, physics, computer science. This is the kind of stuff we are investigating in since 2020, collaboration with Deutsche Börse, which we actually presented 2020 at the 2021 at the Bitkom Summit, and we are attending Bitkom Summit since then every year. So we are talking about here about potentials and risks of quantum computers. And one potential lies in the field of risk analysis for financial institutions, which means bring things from not possible 13 years to within business days possible hours or minutes. We're featured in like several magazines already, RiskNet, which is a known magazine in risk management. And this is actually the software we are going to present today. It's called Geqo, Generic Quantum Operations, and it's a sovereign software stack for quantum technology at scale. And our use cases are in quantum communication, so security assessments of quantum communication protocols, but also in the field of quantum algorithms. So we call it Geqo Core, which is actually open sourced. It's a very lightweight framework to generate quantum circuits and a powerful simulator. We have a Geqo Flow, which is a hybrid workflow engine, so an event-driven workflow engine, because a quantum program will always be an interact of a classical computer and a quantum computer. Doesn't matter if it's in the NISQ era, many people are currently talking about, but also in the fault-tolerant era, where things like error correction, encoding, decoding, and stuff like this comes in. And there is also Geqo Studio, which is a low-code user interface. People can log in and play around with pre-implemented quantum programs, so protocols, do the security assessments, or write quantum algorithms, test them, build them, make them visual, where actually the information flow is, well, the idea and the necessity about this is auditability. Things need to be very clear, for example, in quantum communication. So this is made to be user-centric. The layers we are touching with Geqo is, well, end-to-end down to hardware. So everything that is firmware, we leave with hardware vendors. We are on the application down to the compiler level. So I talked about about Geqo Studio, which is the connecting point. We have this currently deployed on a server, available via browser, can be on-premise, can be on cloud. We are working there with cloud providers. The workflow and integration layer is Geqo Flow. The algorithm layer, we call it Geqo Core, which is like the first iteration open sourced. And this is maybe the most interesting case, current and the most work that needs to be going, is the compiler level and the intersection to hardware. And now we don't have a lot of time. I need to rush a little bit. Tobias will present the first applications for this kind of software.
Yeah, thank you, Niklas. So yeah, we're very excited about Geqo, and maybe let's just dive in with two examples. The first example is quantum key distribution, so it's quantum secure communication. We view this as a first example of a quantum program, because at the end, a quantum program means that we have some quantum circuit that acts on some gates. There's classical pre-processing, post-processing, and that is something that applies to quantum key distribution protocols, but it also applies to, well, the large-scale quantum circuits that Niklas mentioned for risk models in banks or drug discovery or whatnot. So it's the same principle, and this is one first concrete use case. And so to make things concrete, let's imagine we have a QKD line between Berlin, where we're here, and Frankfurt. You are a bank with 2 offices, and you bought this device, and now you want to know how secure is it really. Everybody says that's the stuff to go for, but if you want to know how secure your QKD setup really is, then one way to approach that, and we think it's a very important way to approach it, is to build a digital twin, to build a simulation of that device, including everything about it, all its imperfections, its errors, its noise, because that's what you really need to do penetration testing and security assessment. And the things you learn out of that can then be used to optimize this QKD network, and do all of that before it goes live, before you send the first qubit around. Now, I think it's probably best if I show you how we do that in our program. So here comes a little video explaining what we do.
So this is actually the front end. You log in, and here is how you can quickly build a so-called quantum program.
Now, the example that we just saw was very simple, but it's actually easy in Geqo to extend this. Here is sort of the schematics of how someone would attack a QKD setup. But the real world, of course, isn't that simple. I mean, that's a good illustration, but how do things look like in reality? This is the quantum part of a real QKD setup, and this is when you zoom out and include all the classical pre- and post-processing. You have the raw key generation, you have error reconciliation for the experts, and after that, you have something called privacy amplification. Those are all crucial steps in that protocol. And if you want to have a true digital twin, you will have to be able to simulate all of those. And our software can do it. And you can just click it together quite easily and rapidly as well. So that's how the software looks in practice. Now, what can we do with that? One thing about QKD setups is that they are very, very nice tools for secure communication. But to assess the security, you need to go beyond the idealized models that have been proposed in theory and include all of these imperfections and noise, because that's what attackers are going to use. They are going to exploit these weaknesses of your system to try and get information. And so, as a user, you want to know what actually will be the attacks that an attacker will do on my system. We use quantum machine learning to do the assessment thereof. So more specifically, we put a variable circuit, think for instance about qubit rotations that have some angle that can be varied, into the QKD setup, and then use machine learning. That is what we did together with Bundesdruckerei. We use machine learning to find the optimal attacks. And so this is something that actually brings you added value. What we could show is that using machine learning, we could identify attacks that have never been reported before. That is because the attacks that were previously reported as optimal attacks were done for idealized theoretical models, not for real ones with errors. So this machine learning is really something that is essential if you want to assess the security of QKD. But zooming back out into the global perspective, I said that for us, quantum programs involve, circuits and classical and pre-processing. In all of these tasks, AI will be essential. It will be a big helper, and so we are using it already at this stage and go on into the future doing this. Now, what are some of the things that you would like to do in the future? So think, for example, about forecasting the economic development. That's, of course, a big task. And if you're good at forecasting the economic development, then you can make smart business decisions before your competitors can do. So this is, of course, something that evolves, goes into the field of macroeconomics. It's quite complex. You have different households, industry, fiscal, monetary policy, so different stakeholders, they're all interacting. And then every once in a while, a dramatic event comes along that changes the rules of the game, such as climate change and carbon pricing. And then you want to know what's the impact of that for jobs, for GDP, which sector is going to be affected. And if you know the answers to these questions, then you have a big advantage. But getting these answers is hard. The models that you use, for example, dynamic stochastic general equilibrium models, they are huge and complicated models. And the mathematical complexity there lies in the inversion of matrices. Okay. Now, the matrices in these models, however, they're large, but they're special. They have one special feature, namely lots of zeros. Lots of entries in these matrices are zeros. That's what you see here. That's a graphical representation of the matrix, and only the blue spots are non-zero entries. The rest is zero. So we call these matrices sparse. And if you have a sparse matrix, then you can use a quantum algorithm, the so-called HHL algorithm, to do the matrix inversion for you. I'm not going to walk you through the full example. I'm going to walk you through a baby example so that you see how it works. So here's the baby example. We have a 2x2 matrix. That's two coupled equations, and we have two unknowns, x0 and x1. And so if you want to invert that matrix to find x0 and x1 with a quantum circuit, here is how it goes. You need to first encode that matrix into your qubits, and then you run the HHL algorithm to find the inverse of the matrix. And in the end, you do some measurements of your qubits. And the measurement results, you can then do statistics, they will come with a certain probability that encodes the solutions x0 and x1. This is real data from real quantum computers, in this case from AQT, that we obtained in a project together with Bundesbank. If you want to know more, please have a look at this QR code. There's a longer article relating to it. But the bottom line is that using quantum computers, we can really achieve an exponential scale-up in this particular problem, but also in other problems. And this really is the exciting thing about quantum computing. It's not just securing your communication, it's unlocking new business opportunities and having new ways to make smart business decisions. Niklas.
So, thanks a lot. So, we are trying to turn the potential of quantum into real impact. And how are we doing this? This is our offer. This is what we do with our clients in partnerships, in research models, to come out with relevant technology assessments. So how far is the technology really? What needs to be there in terms of hardware? in terms of fidelity, in terms of qubit count, in terms of connectivity, so the nitty-gritty of the technology, what is really there and what needs to be done. Well, our discovery workshops start with knowledge transfer. What is a qubit? If people are really interested in this nitty-gritty things, but also just educating people about, well, what's the potential and especially what's the risk that are like the most people currently interested in the security business. We do prototyping projects, so what we did with Bundesbank was not only like finding a nice example of a use case, but also building the prototype and then test it on real hardware. So the full end-to-end line, because as a business end user, if you really want to know how far is the technology, can I already gain value of it, you need to have one of these end-to-end prototypes to assess as an example to really find out what's currently possible. And we also do research projects or longer-term collaborations, so 1 to 3 years, 1 to 4 years is actually one project to build and protect IP, because we think this is also a relevant point. We have own IP, we have shared IP, we know how to do this, so yeah, I'm inviting you to do this with us together.